This presentation will delve into discrete and limited dependent variable models. Our session emphasizes the practical aspects of estimation, interpretation, and diagnostics, all demonstrated using the EViews software. As famously stated, econometrics serves as the bridge between abstract economic theory and real-world application. Our objective is to equip you with the essential tools to analyze variables that are not continuous. We'll concentrate on graphical user interface, or GUI-based estimation methods to ensure these advanced techniques are accessible and easily applicable in your work. To understand why these specialized models are necessary, let's first examine the limitations of the standard ordinary least squares approach when dealing with discrete data. Ordinary least squares, or OLS, assumes that our dependent variable is continuous. However, when we're dealing with discrete data, such as a binary choice, like yes or no, coded as 0 or 1, OLS breaks down, leading to biased and inconsistent estimates. A major issue is the logical fallacy of unbounded predictions. As you can see, a linear probability model, which is OLS applied to a 0-1 variable, can predict probabilities less than 0 or greater than 1, which is simply impossible. For example, if we model home ownership based on income, OLS might nonsensically predict a negative 10% chance of ownership for very low incomes, or a 110% chance for very high incomes. Furthermore, the error terms in such models are inherently heteroscedastic and non-normal, violating key OLS assumptions and making our standard inferences unreliable. Finally, the functional form is often incorrect. Many real-world decisions are threshold-based. A choice is made only once a certain condition is met, which a linear model cannot accurately capture. Since OLS is clearly not suitable for these scenarios, we need a different set of tools. Let's now explore a map of appropriate models based on the nature of our dependent variable. To effectively choose the right econometric model, the most crucial first step is to start with your data and thoroughly understand the nature of your dependent variable, y. Rather than memorizing complex formulas, focus on identifying the specific data type you are working with. If you can clearly identify the shape and characteristics of your dependent variable, the appropriate modeling method will follow automatically. For instance, if your dependent variable is a binary choice, like a yes-no or 0-1 outcome, you'll utilize binary models, such as Logit or Probit. When dealing with variables that have a natural ranking, but where the intervals between categories are not necessarily equal, like survey responses on a scale, ordered models are the suitable approach. If your variable is continuous but has a significant pileup at a specific value, often 0, representing a corner solution, then a Tobit model is required. For situations where observations are missing due to a non-random selection process, the Heckman selection model helps correct for potential bias. Finally, for dependent variables that represent non-negative integers, such as counts of events, you will employ count models. This systematic approach ensures you apply the correct tool for your analytical task. Let's start by diving deeper into the most common case, binary dependent variables. The core idea behind Probit and Logit models, used for binary dependent variables, is the concept of an unobserved latent variable. Let's call it y star. This variable represents an underlying propensity, or net utility. We model y star as a linear function of our explanatory variables plus an error term. We don't directly observe y star. Instead, we observe a binary outcome, y equals 1 if y star crosses a certain threshold, typically normalized to 0, and y equals 0 otherwise. The key distinction between these models lies in the assumed distribution of this error term. The Probit model assumes errors follow a standard normal distribution, while the Logit model assumes a logistic distribution, which has fatter tails, giving more weight to extreme outcomes. The Gompit model uses an asymmetric distribution, which can be particularly useful for rare events. When it comes to model selection, Logit and Probit models often yield very similar results in practice. Logit is frequently preferred for its interpretability through odds ratios, while Probit is favored when errors are strictly normally distributed. First, it is crucial that your dependent variable is coded correctly. EViews requires the binary variable to be strictly coded as 0 and 1. Using texts like yes/no or other numbers like 1/2 will result in an error, so ensure your data is properly formatted before you begin. To estimate a binary model in EViews, you'll start by navigating the menu to Quick, then selecting Estimate Equation. Within the estimation dialog box, change the method from the default ls to binary for binary choice models. Next, you will specify your equation by listing the dependent variable, followed by C for the intercept, and then your chosen regressors. For example, to model whether a person is in a union based on their age and education, you would specify union C age education. Finally, choose your preferred estimation method, typically between Logit and Probit, at the bottom of the dialog box. Once you've clicked OK and run the estimation, the next critical step is understanding the output table that EViews produces. When examining the output from a binary estimation, like this Logit model from EViews, it's crucial to understand how to interpret the results correctly to avoid common pitfalls. The most frequent mistake is interpreting the coefficients as direct marginal effects on the probability. They are not. A coefficient sign simply indicates the direction of the relationship, but its magnitude does not directly tell you the change in probability for a one-unit change in the explanatory variable. For instance, coefficient as 0.028 for age does not mean a 2.8% increase in probability. Instead, we rely on the z-statistic, which functions similarly to the t-statistic in OLS, to assess the statistical significance of individual coefficients. Pseudo-R-squared measures, such as McFadden R-squared, are used for overall model fit, but remember, these values are typically much lower than traditional R-squared in linear regression. A value between 0.2 and 0.4 is often considered quite good. Finally, the likelihood ratio, or LR statistic, tests the joint significance of all regressors in the model. Always remember, the effect of an independent variable in a binary model is nonlinear and depends on the specific value of that variable. Ordered models are designed for dependent variables that have a natural ranking, but where the distances between the categories are unknown. Classic examples include Likert scales, like strongly disagree to strongly agree, or credit ratings such as AAA or A. Similar to binary models, we assume an underlying latent variable y star. The observed categorical outcome depends on which range, defined by estimated cut points, this latent variable falls into. A core assumption of these models is the parallel regression assumption, which states that the slope coefficient is constant across all categories. Only the intercepts, or the cut points separating the categories, are allowed to change. For estimation in EViews, it's crucial that your dependent variable is coded as numeric integers, such as 1, 2, 3, and so on, to represent these ranks. We now turn to understanding limited dependent variables, and it's crucial to distinguish between censored and truncated data. With censored data, we observe the independent variables, or x, for all individuals. However, the dependent variable, y, is limited or constrained for some, often resulting in a noticeable pileup of observations at a specific limit, such as 0. For example, in a survey on luxury spending, we might observe everyone's income and demographics, but many individuals will report 0 spending, creating this pileup at y equals 0. In contrast, with truncated data, we don't observe either x or y for a portion of the sample. It's as if a whole slice of the data is completely missing from our spreadsheet. Imagine a survey specifically targeting high earners, where data for anyone below a certain income threshold is simply not collected. A simple heuristic to tell them apart is to ask, do we see the X? If you can see the characteristics of people who didn't participate or had a 0 outcome, it's censored. If those people are totally missing from your dataset, it's truncated. The most common type of limited dependent variable model is the Tobit model, which specifically deals with censored data. Let's look at how to estimate it. When working with limited dependent variables in EViews, both Tobit and truncated models are estimated using the censored method within the equation estimation dialog. A crucial step is defining the boundary or limit. For instance, in a standard Tobit model where your variable is left censored at 0, you would input 0 in the left censoring point field and leave the right completely blank. Leaving a limit field blank in EViews indicates that there is no boundary in that particular direction. Furthermore, EViews offers the flexibility of specifying variable limits. If your censoring point varies across observations, perhaps due to a policy, like a benefit cap that depends on family size, you can simply enter the name of the variable representing that limit instead of a fixed number. This allows for highly customized model specifications to accurately reflect your data's characteristics. The Heckman selection model, often called Hecket, is crucial for addressing selection bias. This bias arises when we only observe an outcome for a non-random subgroup of the population. A classic example is estimating wages. We only observe wages for individuals who choose to work, not for everyone. If the decision to work is systematically related to factors that also influence wages, a simple OLS regression on just the working sample will produce biased results. The Heckman model tackles this in two stages. First, a selection equation, typically a binary Probit model, predicts the probability of an individual being in the observed sample, for instance, the decision to work. From this first stage, we derive a correction factor known as the inverse Mills ratio, denoted by lambda. This lambda term mathematically captures the influence of the selection process. In the second stage, we estimate our main outcome equation, such as a linear wage model, but we include the calculated inverse Mills ratio as an additional regressor. This inclusion corrects for the inherent selection bias. The crucial diagnostic test is to examine ρ, the estimated correlation of errors between the two equations. If ρ is not statistically significant, it implies there's no significant selection bias, and a standard OLS model would have been perfectly adequate. To perform Heckman estimation in EViews, you'll select the Hecket method from the equation estimation dialog. This model requires you to specify two distinct equations: the selection equation, which models the decision to participate or be observed, and the response equation, which is your main outcome of interest. For example, the selection equation might explain labor force participation, while the response equation models wages. A crucial aspect for the model's identification is the exclusion restriction. This means the selection equation must include at least one variable, like kids in our example, that is not present in the response equation, such as wage, C, educate, expr. This variable should theoretically influence the selection decision, but not directly impact the outcome. EViews provides two estimation types: the robust two-step method, which is often the default and a good starting point, and the more efficient maximum likelihood method, which relies on stronger distributional assumptions. Count data models are specifically designed for dependent variables that represent non-negative integers, such as the number of patents a company holds, the frequency of doctor visits, or the occurrence of accidents. The most common starting point is the Poisson model. However, the Poisson model makes a very strong assumption known as equidispersion, meaning that the mean of the distribution is equal to its variance. In real-world economic and social data, we frequently encounter a phenomenon called overdispersion, where the variance significantly exceeds the mean. If ignored, overdispersion can lead to incorrect standard errors and unreliable statistical inferences. To address this, the negative binomial model is typically a much safer and more flexible alternative. It explicitly accounts for overdispersion by allowing the variance to be greater than the mean, making it more suitable for the skewed distributions often seen in count data. Next, let's explore how to implement and interpret these models effectively in EViews. To estimate count models in EViews, you simply select Count as your method. Within this setting, you have the flexibility to choose between the Poisson model, the negative binomial model, and other specialized options. A critical feature for ensuring the reliability of your results is the quasi-maximum likelihood, or QML, option. Activating QML provides robust standard errors, which is immensely beneficial because it safeguards your statistical inferences even if some strict distributional assumptions of the model, like the Poisson model's mean variance equality, are not perfectly met. Regarding interpretation, the coefficients from these count models hold a semi-elasticity meaning. For instance, a coefficient of 0.10 for a particular variable implies that a 1-unit increase in that variable is associated with an approximate 10% increase in the expected count of the dependent variable. When evaluating the discrete and limited dependent variable models we've discussed, traditional metrics like the standard R-squared are largely uninformative. Instead, we shift our focus to more practical measures. A key diagnostic is the percent correctly predicted, which you can derive from the expectation prediction or classification table. This table shows how accurately your model classifies actual outcomes. For instance, if your model correctly predicts 80% of the actual outcomes, it demonstrates significant value, irrespective of a low pseudo-R-squared. Pseudo-R-squared values in these contexts are typically much lower than an OLS, so don't obsess over them. For comparing different models, especially non-nested ones, information criteria like AIC and BIC are invaluable. We also have specific tests, such as the Andrews-Hosmer-Lemeshow test for goodness of fit in binary models, and the standard likelihood ratio test for checking redundant variables within your specification. We're examining a case study on labor supply using the MRAS data, with an objective to estimate the probability of a woman joining the labor force, a binary outcome. However, before modeling, it is crucial to understand the structure of our variables. As highlighted in our practice tips, we must always run descriptives first. Our action plan involves viewing descriptive statistics, checking for binary structure, and visualizing the distribution with a histogram. Applying this, if we look at the hours variable, the descriptive statistics show a mean of approximately 740.58 hours, with a minimum and median of 0. The presence of decimals and a mean far from between 0 and 1 immediately tells us this is not a binary variable. The histogram visually confirms a significant pile-up at 0, indicating a large number of observations where women report working 0 hours. This characteristic, where a continuous variable is censored at a specific limit like 0, strongly suggests that a Tobit model would be the appropriate choice for analyzing hours, because it specifically handles such censored data distributions. This rigorous data exploration prevents us from applying an incorrect model. To summarize the EViews toolkit for discrete and limited dependent variable models, the fundamental principle is to correctly match the model to your data structure. For 0-1 binary outcomes, such as yes or no decisions, you'll use the binary method in EViews, typically employing Logit or Probit models. When your data represents a ranking with a natural order, like survey responses on a scale of 1 to 3, the ordered method is appropriate. If your dependent variable exhibits a corner solution, meaning it has a pile-up of zeros combined with continuous positive values, you should select the censored method for a Tobit model. For situations where you have a missing sample due to a specific selection process, the Hecate method is necessary to correct for potential bias. Lastly, for integer count data, such as the number of events, you will use the count method, often opting for the negative binomial model to address over-dispersion. Ultimately, remember that specification is key. EViews simplifies the estimation process, but the choice of model and its correct specification relies heavily on your economic intuition and a deep understanding of how your data was generated. To conclude our session, I want to provide you with some valuable resources for further study and practice. Our references include foundational texts like Green's econometric analysis and Wooldridge's econometric analysis of cross-section and panel data, which are excellent for a deeper theoretical understanding. Additionally, the EViews User's Guide 2 offers specific guidance on advanced single equation analysis within the software. For more practical tutorials and datasets, I encourage you to connect with Vietlod Econometrics via our website, www.vietlod.com, or our YouTube channel. Finally, as a quick reference, we have a syntax cheat sheet for EViews. You'll see examples for estimating a binary model, a left-censored model like Tobit, where the dependent variable hours is censored at 0, and a Heckman selection model for wage, which includes INELF, age, and kids in the selection equation. Thank you for joining our discussion on discrete and limited dependent variable models. We've covered the nuances of choosing the right econometric tool for various data